In this video, we're going to work example problems related to trig functions of acute angles. Now, every right triangle has two acute angles, so a lot of these problems are related to finding trig functions of just angles in just a random general right triangle. Okay, match each trigonometric function in column 1 with its value in column 2. Choices may be used once, more than once, or not at all. So what this problem is about is there are a few specific acute angles that are very common. That's 30, 60, and 45 degrees. So we studied the trig functions of those angles in a little more detail than just a general acute angle. Okay, and what we learned is that for a 30, 60, 90 right triangle, the side lengths are going to be proportional to these side lengths. These are like the base side lengths that are used as a reference for a 30, 60, 90 triangle. Okay, and for a 45, 45, 90 triangle, right triangle, the side lengths are going to be proportional to these side lengths like this. Again, these are like reference side lengths. Now, but the idea is, though, that any like 30, 60, 90 triangle, no matter what the side lengths are, is going to be similar to this triangle. So similar triangles have the same trig function values because similar triangles have the same angles, right? Similar right triangles have the same trig function values because similar triangles have the same angles, and similar triangles, the side lengths are all of the same, they're all the same proportion. And so we can calculate the sine of 30 or the sine of 45 or any trig function value of these angles directly from these triangles. So, okay, sine of 30 is opposite over hypotenuse. That's 1 over root 3. Multiply that by root 3 over root 3, and you get root 3 over 3. So 1 matches with F. Okay, let's do what about cotangent of 30? That would not opposite over adjacent, but adjacent over opposite. That's root 3. Okay, there's no other 30. All right, what about 60? Secant of 60. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so hypotenuse over adjacent, this would be 2. Okay, what about cosecant of 60? That's the reciprocal of sine, so hypotenuse over opposite, 2 over root 3. Root 3 over 3. Okay, tangent of 45, opposite over adjacent, is 1. Cosine of 45 is adjacent over hypotenuse, so 1 over root 2. That's going to be root 2 over 2. Okay, and sine of 30, I don't know how did I get? Sine of 30 is opposite over hypotenuse is 1/2. So this should be 1/2. Okay, and there we go. So they say more than once. I'm not sure what they mean. Yeah, I guess you could potentially have like the same, the sine of 45 and the cosine of 45 are the same thing. But these are functions, right? These aren't going to map to two different outputs. But you could have the same, they're saying you more than once, you could have the two different functions mapped to the same output. All right, find exact values or expressions for sine A, cosine A, and tangent A. So, yeah, when it comes to analyzing trig functions of acute angles, we can think about the standard definition, right? Here's for theta measured from the standard position. Here are the acute angles, but we also think about it from the standpoint of we could just be presented with a right triangle in any orientation in 3D space. You have some plane here, it's whatever, and you have a triangle that maybe we could even draw it like upside down, alpha, beta, And you could just do, you're looking down at it like this. You could do the trig functions on those two acute angles. Opposite over hypotenuse, adjacent over hypotenuse, the SOHCAHTOA. So here, the angle A, what's the sine? SOHCAHTOA, opposite over hypotenuse. That's it. That's the exact value. Right? It's not like a decimal or anything. It's a fraction. It's an exact value. All right. What's the cosine of A? Adjacent over hypotenuse. SOHCAHTOA. Okay. Are these simplified? Yeah. You can't. This is fully reduced. Okay. What is the tangent of A? Opposite over adjacent. Okay. They just have the side lengths as with variables, but same thing, easy. Sine of A is opposite over hypotenuse. Cosine of A is adjacent over hypotenuse. Tangent of A is equal to opposite over adjacent. Suppose ABC is a right triangle with sides of lengths lowercase a, lowercase b, and lowercase c in right angle at uppercase c. Use the Pythagorean theorem to find the unknown side length. Then find exact values of the 6 trigonometric functions for angle B. Rationalize denominators when applicable. Okay, so we're given A and B. We're going to find C, and then with that, we've got the 3 side lengths. We can find trig function values of either of the angles, but we're going to be evaluating the trig functions of angle B. And so here's something that's different from the general definition. It's hard to see how, angle A here, if we're finding trig function values of angle A, well, this is already in like standard position, but this angle is upside down, but it doesn't matter. With any right triangle in any orientation, you can come to one of the acute angles and do SOHCAHTOA. So that this is what kind of an application that kind of strays from the general standard definition of trig functions, right? When you're talking about angles measured from standard position, just the general definition, this is a different application. You can come to any acute angle in a right triangle, no matter how it's oriented, and just do SOHCAHTOA on that angle. All right, so Pythagorean theorem, a squared plus b squared is equal to c squared. So 25 plus, that's 5 squared, 12 squared is 144. So this is going to be C. Square root of 169 should be 13. Okay, there we go. So what is sine of B? Opposite over hypotenuse, that's B over C, so 12 over 13. What is cosine of B? Adjacent over hypotenuse, that's A over C, so 5 over 13. What is tangent of B? Opposite over adjacent, that's B over A. All right, so we can now use the reciprocal identities to get cosecant, secant, and cotangent. So just flip the values. It's not beta, it's B. Okay, there we go. All right, same type of problem. So we need to solve for B here. So we've got A squared plus B squared is equal to C squared. So B squared is equal to 49 minus 36 is 13. We're not going to need to do plus or minus because we know that the side lengths of this triangle are going to be positive. So positive root 13. Okay, so we've got the side lengths of the right triangle. So what is sine of B? Opposite of hypotenuse, that's B over C. Okay. Cosine of B is adjacent of hypotenuse, that's A over C. Okay, now tangent of B is opposite over adjacent, B over A. Okay, so secant of B is 7/6, and now we're going to have to rationalize here. So cosecant of B is 7 over root 13. So times root 13 over root 13 is 7 root 13 over 13. All right, cotangent of B, 6 over root 13 times root 13 over root 13. So that would be 6 root 13 over 13. Okay, so we need to solve for B. A squared plus B squared is equal to C squared. So B squared is equal to 100 minus 9 is 91. So B is equal to root 91. Okay, so what is sine of B? That's going to be opposite of hypotenuse, so root 91 over 3. Cosine of B is adjacent of hypotenuse, A over C. Okay, tangent of B, opposite over adjacent, B over A. Okay, secant of B is 10/3. Cosecant of B is 3 over root 91. So times root 91 over root 91, that's going to be 3 root 91 over 91. Cotangent of B, 3 over root 91. Oh, okay, same thing. Is that right? No, that's not right. So opposite over adjacent. So this is right. But this is not right. Sine of B is opposite of hypotenuse. That's going to be root 91 over 10. So 10 root 91 over 91. Okay, solve for B again. So A squared plus B squared is equal to C squared. So B squared is equal to 3. So B is equal to root 3. So sine of A is opposite over hypotenuse. That's root 3 over 2. We're doing B here. Cosine of B is equal to adjacent over hypotenuse A over C, so 1/2. Tangent of B is opposite over adjacent, B over A, so just root 3. Okay, so secant of B is 2. Let's see, cotangent of B is 1 over root 3, which is going to be root 3 over 3. And then cosecant B is 2 over root 3 times root 3 over root 3 is going to be 2 root 3 over 3. All right, A squared plus B squared is 4 is equal to C squared is 25. A squared is equal to 21. So A is equal to root 21. So sine of B is equal to opposite of hypotenuse, so B over C. That's 2 over 5. So we've got cosecant b is 5/2. Cosine of b is equal to adjacent over hypotenuse, so a over c, so root 21 over 5. Tangent of b is equal to opposite over adjacent, so b over a. 2 over root 21 times root 21 over root 21, so 2 root 21 over 21. Okay, so cotangent of b is adjacent over opposite, so lowercase a over lowercase b, so root 21 over 2. And secant of b, 5 over root 21 times root 21 over root 21, so 5 root 21 over 21. Write each function in terms of its cofunction. Assume that all angles labeled theta are acute angles. All right, so cofunctions. How do cofunctions work? Well, the idea is for a right triangle, if we've got, let's say, this angle is beta and this angle is alpha, and you've got sides, so A, B, C. Well, the cosine of beta is what? B over C, right? So cosine of beta is B over C, but what is the sine of alpha? That's also B over C. So this is true, right? For any right triangle, you can relate the two acute angles this way. But then for any right triangle, the two acute angles are also complements. So you could do this. You could say cosine of beta is equal to sine of 90 minus beta. Or you could have done it the other way. You could say cosine of 90 minus alpha is equal to sine of alpha. So cosine 90 minus alpha is equal to sine of alpha. Or if you wanted if you wanted to do, okay, so sine of beta, then you could say that's cosine of 90 minus alpha. If you want to, you could do it however you want. And so because it works this way with cosine and sine, these are called cofunction pairs. And there's two other cofunction pairs. You could do this with, so tangent of beta, you notice, is equal to cotangent of alpha, right? Tangent of beta opposite over adjacent. Cotangent of alpha is adjacent over opposite. They're both A over B. So you could do kind of the same deal with tangent and cotangent, but then it's the same with secant and cosecant. You could do any of these kind of cofunction identities you want. Because, okay, so secant of beta is hypotenuse over opposite, C over A. Cosecant of alpha is hypotenuse over adjacent, C over A. Yeah. So that's the idea of the cofunction. So we just, okay, so cosine of 30, what's its cofunction pair? It's sine. Just do 90 minus 30. That's it. Okay, cosecant, what's cosecant's cofunction pair? It's secant. 90 minus 60. That's it. Secant's cofunction pair is cosecant. What is 90 minus 39? So 90 minus 40 is 50, so this would be 51. Okay, its cofunction pair is cosine. So let's see, 90 minus 38.7. So 51.3. All right, we're assuming that theta here is an acute angle. So the cofunction pair of secant is cosecant. And all we're going to do is, so 90 minus this entire angle. You got to get that right. Don't do this. No. No, because you're not subtracting 90, or you're not subtracting the entire angle from 90. So this is 90 minus theta minus 15. This is 75 minus theta. So find one solution for each equation. Assume that all angles involved are acute angles. So, okay, yeah, they're saying one solution because when you think about coterminal angles, you could potentially find more than one solution. So they're wanting us to focus on one solution, and we're going to do this with the cofunction identities. So we know that this is a cofunction pair, so the tangent of whatever this is going to be equal to the cotangent of, well, okay, no, what we want to do is we can convert cotangent of alpha plus 10 to the tangent of something. Well, that's going to be what? You just do, it's a cofunction pair. You just do 90 minus, so 90 minus alpha minus 10, so 80 minus alpha. So this is equal to 80 minus alpha. So now we can set these two equal to each other. The alpha is equal to 80 minus alpha. So alpha is equal to 80 minus alpha. So 2 alpha is equal to 80. So alpha is equal to 40. Okay, same idea. Let's convert one of these. These are cofunction pairs, so we can convert either this cosine or this sine to cosine or sine, and so then we can set the arguments equal to each other. So we can say that cosine of 3 theta minus 20 is equal to sine of what? You just do just 90 minus, do that. So it's going to be 110 minus 3 theta. So this is equal to sine of 110 minus 3 theta. So we can set these equal. Sine of this is equal to sine of this. So 2 theta plus 10 is equal to 110 minus 3 theta. So 5 theta is equal to 100. So theta is equal to 20. Okay, same process. So I'm going to convert cotangent to tangent, but you could just as easily convert tangent to cotangent. So cotangent of 5b minus 10 is equal to tangent of, so we want to do 90 minus this entire angle. So 90 minus 5b plus 10 is 110 minus 5b. So okay, now let's set 3b plus 4 equal to 110 minus 5b. Add 5b to both sides. 8b, subtract 4 from both sides. Divide both sides by 8. So 106 divided by 8. Let's see, do that? Oh, no, I see. Okay. 90 plus 10 is 100, not 110. So 100 minus 5b. 100 . So 3b plus 4. All right, so 8b is equal to 96. 96. So b is equal to 12, and this would be in degrees because, you can't. 5 is just like a number. So 5 times this needs to be in degrees, and you can subtract degrees from degrees and get an argument. So these answers would be in degrees. Okay, so we've got so cosine of 2 theta plus 5 is equal to sine of, these are cofunction pairs, so 90 minus 2 theta plus 5, that's 90 minus 2 theta, so 85 minus 2 theta, so okay, we've got theta minus 20 is equal to 85 minus 2 theta. Add 2 theta to both sides. Add 20 to both sides. So theta is equal to 105 divided by 3 is 35 degrees. Okay, these are cofunction pairs, so cosecant beta plus 8 is equal to secant of, so 90 minus beta plus 8 is 90 minus beta minus 8. That's 82 minus beta. So this is equal to secant. All right, so 3 beta plus 10 is equal to 82 minus beta. Add beta to both sides. Subtract 10 from both sides. So $18 degrees. Okay, determine whether each statement is true or false. Is sine of 50 greater than sine of 40? Well, we could think about this either by thinking about a right triangle or using the general definition. To me, the general definition is easier. So, we've got an acute angle here. As theta gets bigger, you're getting a larger ratio. Like sine goes from 0 when theta is equal to 0 to 1 when theta is equal to 90. So sine, this is true, right? As theta gets bigger, the y gets bigger. The proportion of y to the radius is getting bigger. Okay, well, let's get a permanent, because these are all going to be acute angles, so I'll just leave this up here. Okay, so is sine of 46 less than cosine of 46? We could use let's use the cofunction identity. So this is saying, is sine of 46 less than sine of what is 90 minus 46? That's 44. Yeah. Or no, not less than, so no, false. As far as acute angles go, the greater the angle, the larger sine is going to be. So this is false. Sine of 46 would be greater than sine of 44, so that means that sine of 46 would be greater than cosine of 46. Okay, let's use the cofunction identity again. This is asking, is tangent of 41 less than tangent of 90 minus 41 is 49? Okay, so tangent is opposite over adjacent. So as theta gets bigger, x is getting smaller, y is getting bigger, so tangent's getting bigger. So going from 0 to 90, as theta gets bigger, tangent's going to get bigger, so this is true. Okay, is secant 60 greater than secant 30? So what is secant? That's the reciprocal of cosine, so that's going to be r over x. As theta is getting bigger, x is getting smaller, so secant's getting bigger. Or no, as theta is getting bigger, x is getting smaller, r is just kind of like a finite value. So like this goes as theta approaches 90, secant is going to infinity. So but then as theta approaches 0, secant is going to 0 secant's going to 1, r, because x is approaching r. So you're going from 1 to infinity, which means that the larger, for acute angles, the larger the angle, the larger the secant. So this is true. All right, find the exact value of each expression. So these questions are dealing with the special angles 30, 45, and 60. So let's go ahead off to the side and draw those base triangles. So here's the 30, 60, 90 triangle. So this was 2, 1, root 3, and then the 45, 45, 90. We've got 1, 1, root 2. All right, so what is tangent of 30? That's opposite over adjacent, so that's 1 over root 3 times root 3 over root 3. That's going to be root 3 over 3. Okay, what is sine of 30? And just remember, we can, for any 30, 60, 90 triangle, even if the legs aren't these same lengths, like it's there, no matter what, you're going to have similar triangles, so these proportions aren't going to change. Like you could, no matter what size of the triangle, this leg here that's adjacent to the 60-degree angle is going to be half of the hypotenuse. For no matter what, if you have a 30, 60, 90 triangle, no matter what the size is, these could be miles long, whatever. This leg, if it's 30, 60, 90 degrees, that's the angles, this leg adjacent to the 60 is going to be half of the hypotenuse. No matter what the 45 degree 90 triangle is, no matter how big it is or small it is, whatever, this leg's going to be equal to this leg, and the hypotenuse is going to be root 2 times these two legs. And so because of that, because trig functions are based on like proportions of sides, then and with similar triangles, that's what's not changing. The proportions aren't changing. We could just, for the sine of 30, you could be dealing with building a bridge or something, whatever. And you've got some right triangle that's, with random dimensions, and you want to calculate trig values of the angles, you can just pull this triangle out because the proportions are the same. Okay, so the sine of 30 is, you come to the 30-degree angle, opposite of hypotenuse, that's 1/2. Secant 30, secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so hypotenuse over adjacent, 2 over root 3 times root 3 over root 3, that's 2 root 3 over 3. Okay, cosecant of 45, so that's the reciprocal of sine, but I guess it probably wouldn't matter in this case. Like sines and cosines are the same here. So the reciprocal of, so sine is opposite of hypotenuse, so hypotenuse over opposite, this is going to be root 2. Yeah, and so in this situation, secant of 45 is going to be the same as well. Cosine and sine are the same, and secant and cosecant are going to be the same for 45 degrees, right? Because cosine adjacent over hypotenuse, sine opposite over hypotenuse, secant hypotenuse over opposite, cosecant hypotenuse over opposite. Okay, cosine of 45, adjacent over hypotenuse. 1 over root 2 times root 2 over root 2 is root 2 over 2. Okay, tangent 45, opposite over adjacent, this is 1. Sine of 60, opposite over hypotenuse, that's root 3 over 2. Tangent of 60, opposite over adjacent, this is root 3. All right, find the exact value of the variables in each figure. So we want to find what x, y, z, and w are. All right, well, we can see that this is 90, so we've got two right triangles here. We know that this is going to be 30, because if it's going to be a 30, 60, 90 triangle, and that this is going to be 60. Okay, so the 30, 60, 90 base triangle okay. So, again, the idea is for any 30, 60, 90 triangle, like the leg that's connected to the 60-degree angle is going to be half the hypotenuse. So this leg is going to be half of 9. So y is 9 halves. And okay, but now this leg isn't half of w because this is connected to the 30. Z is half of w. So z is w divided by 2. Well, here's one of the answers. Okay. And now what we can use the Pythagorean theorem to get x, right? So let's do that. So x squared plus y squared, so 81 over 4, is equal to 81. So x squared is equal to, let's see, 81 minus, so 243 divided by 4. And if we take the square root of that, 9 root 3 over 2. So x is 9 root 3 over 2. So, okay, there we go. Now, we know that, and just note that, so I said z was w divided by 2, but you could have done, we could have said, like, use trig functions, right? So, like, the sine of 30 is equal to z over w, right? And so, but what's sine of 30? It's 1/2. So 1/2 is equal to z over w, and you get w is equal to 2z, or you see what I mean? Or z is equal to w over 2. We could have done it that way. So like we could just say, okay, the cosine of 60, we could see, is equal to what? Well, okay, we don't want to do that. Let's do we'll get the same equation. Let's do the cosine of 30 is equal to adjacent over hypotenuse. That's y over w. But what's cosine of 30? It's root 3 over 2. So let's solve for w. So you've got w root 3 over 2 is equal to 2y. So w is equal to 4 over root 3y. But we know that y is 9 halves, so okay, times root 3 over root 3. So 18 root 3 over 3. So 6 root 3. That's w. Okay. So that means that z is 6 root 3 divided by 2. That's 3 root 3. So z and there we go. I messed this up. This shouldn't be, this should just be y here. And then you've got, so w is equal to 2y over root 3. Okay, but y is equal to 9 over 2, so that's 9 root 3 over 3. So w is equal to 3 root 3. So now z then is, 3 root 3 divided by 2. So okay, there we go. There are the 4 values. Okay, so here we can see we've got a 30, 60, 90 triangle there and a 45, 45, 90. So let's, 30, 60. So we've got 1, 2. So 1, 1, root 2. Okay, so with this 45, 45, 90 triangle, we can see that P is going to be 15, right? P is going to be equal here, so P is 15. But then what is R? R is just going to be 15 root 2. Now, again, you could apply the trig functions and you get the same values, but that's the idea. The proportions are the same, okay? So now Q and T, well, let's just use the proportions. So we know that the angle that's connected to the 60-degree angle of a 30, 60, 90 right triangle is going to be half the hypotenuse. So that means Q is going to be half of R. That's 15 root 2 divided by 2. Now T, we could use the Pythagorean theorem. We could use, like, take the sines, the trig functions of the angles, whatever. So, I mean, let's just use proportions again. So what is this leg, the longer leg of a 30, 60, 90 triangle is root 3 times the shorter leg. This is the longer leg. So, or no, wait. I screwed this up. Hold on. No. I screwed it up because T is the hypotenuse. So this is, okay, yeah. So we've got, well, the R was right. Okay, but now this is, so this is the longer leg. This is the root 3 leg. And so we could, to get Q, we could divide this leg by root 3, right? So 15 root 2 divided by root 3 times root 3 over root 3 is 15 root 6 over 3. So Q is equal to 5 root 6. Okay, now the hypotenuse is twice this leg connected to the 60-degree leg. So T is going to be 10 root 6. See? And there's the 4 variables.